Okay, so what I want to do is I want to spend the next half hour or so talking about work that we've done in my group at Caltech over about the last decade to understand the history of the delivery of extraterrestrial matter to the Earth using helium-3 as a tracer. And this is a project, as I said, that's been going on for some time. It involves a number of collaborators whose names I've listed there. And these collaborators, if you don't know who they are, I'll just say they bring to the table many different kinds of skills necessary to put this project together. So I really couldn't have done it without them. As an outline of what I'll talk about, give you a brief background on cosmic dust and using helium-3 as a proxy tracer of the flux of this dust to the Earth. And then I'll show you the record that we've obtained spanning the last 72 million years, demonstrating that there are important events recorded in the helium-3 signal sediments that include an asteroid collision 8.2 million years ago. And what we originally proposed was a comet shower at 35 million years ago. And I'll conclude with a discussion of a reconsideration of that event at 35 million years ago that was driven by several geochemical observations, as well as a suggestion that was made that instead of a comet shower, this was actually the signal of a large number of impacts occurring on the Moon. So first, the background on the cosmic dust. Cosmic dust is the smallest size fraction of extraterrestrial matter that accretes to the Earth. It ranges from about 3 microns to about 1,000 microns in diameter. The annual flux is about 40 million kilograms per year, which sounds like a lot when you say it, but when you divide it by the surface area of the Earth, it's really a very small amount of material. The composition of this dust is, as you'd expect, just like what you find in meteorites, as shown on the right. It consists of olivine, kerosene, iron, and carbon. The whole typical assemblage that you get in meteorites. And this is known, for example, because these particles are captured in the stratosphere. The image on the left is actually an SEM photograph of about a 7-micron cross-section particle collected in the stratosphere. And one really important point about this size class of extraterrestrial particles is that they have different orbital characteristics, different orbital dynamics than large objects because of the interactions of these small particles with sunlight. It's a phenomenon of the pointing Robertson ray, which causes the particles to slow down in their orbits and spiral into the sun on a relatively short time scale that is less than about 10 to the 5th years, depending on the particle size. The smaller the particle size, the faster they're stripped out of the solar system. So what this tells you, since there is presently a flux, it must mean that this flux is being continuously resupplied. And the process of resupply is the process that I'm most interested in because it tells you about important things occurring in the solar system. The dust comes from the two logical sources that you can think of. It comes from the asteroid belt, where the asteroids are orbiting relatively high velocities relative to each other and in close proximity. There's some probability that they will collide and produce dust. That dust will be swept into the sun, and some of it will accrete to the Earth. Sorry. So the dust comes from collisions in the asteroid belt, and it also comes from active comets. And the images on the bottom are infrared images showing the thermal emission from essentially the silicate fraction coming off of comets that are devolatilizing. Now, it's unlikely that a single comet would produce a significant amount of dust to be detected on the Earth, but there are time periods when we would expect that there would be a greatly enhanced abundance of comets. And one of those kinds of time periods is a shower of comets. So these are events which are known on theoretical grounds, and the evidence that I'll show you, I think, is some of the strongest evidence that they actually occur. The phenomenon is pretty straightforward. Comets orbit stably in the Oort cloud, but they're just barely gravitationally bound to the sun. And over geologic time, there's a probability that stars will pass close by our solar system and perturb the orbits of the comets and cause them to become Earth-crossing, as shown on the diagrams on the right. Now, during comet showers, there will be many millions or even tens of millions of comets active simultaneously. So this is a very major event if there is a close stellar encounter. This particular variety of comet showers is called an impulsive perturbation by an encounter with a passing star. And I'll return to this concept a little later. So the cosmic dust has been collected in a number of different ways. The first recognition that one could find cosmic dust in the geological record comes from the Challenger expedition in 1872, when the naturalists on board the ship collected red clays from the Pacific, and they identified small melt globules and correctly identified them as melted micrometeorites. These micrometeorites are also found, for example, in great abundance in the South Pole water well, where there are essentially lag deposits after the water is removed. And as I mentioned, the particles can also be collected from the stratosphere by the U-2 or the ER-2 aircraft. They essentially just put a sticky plate on the front of the wings, and particles collide with the sticky stuff and can be returned to the lab for study. So one could potentially learn about the flux of cosmic dust through time by simply looking at particle variances. This would be an extremely difficult way to do it because the number of particles is very, very small. So one turns to geochemistry for a solution to this problem to find a proxy for cosmic dust. And a very good proxy for the cosmic dust is helium-3. So now let me tell you a little bit about helium and why it actually tells you something about cosmic dust. The two isotopes. Helium-4 is the alpha particle produced by uranium and thorium decay. It's in relatively high abundance on the Earth. In contrast, helium-3 is in very low abundance on the Earth, partially because it is not produced in substantial amounts by radioactive decay. There are two nuclear mechanisms which produce it. There's cosmic ray spallation and interactions between lithium-6 and neutrons. These are both relatively rare nuclear reactions. So helium-3 is not produced substantially. However, both isotopes are not gravitationally bound to the Earth. So helium is unique among the elements in that it is not gravitationally bound. So the last 4.5 billion years of planetary evolution has acted to strip helium, and in particular helium-3, out of the Earth into the atmosphere, and then it's not gravitationally bound, so it gets lost. So the Earth is extremely depleted in helium-3 compared to bulk extraterrestrial matter. And in one sense, this is a lot like iridium, except for a different reason. If iridium was stripped to the core, helium was stripped into space. And this means that they are potentially useful as indicators of extraterrestrial matter. In addition, the beauty of the helium system is that we have two isotopes, so we can use an isotopic technique to prove that the helium that we're looking at is in fact extraterrestrial. This turns out to be a real problem for iridium. You can't actually always tell when the iridium is extraterrestrial. Helium you can. So net result, helium-3 is a very sensitive tracer of the extraterrestrial component in sediments, and sedimentary rocks carry a record of the accumulation rate of extraterrestrial matter through time. Neither of these is a new idea. Going back as far as 1964, Craig Merrihew had analyzed red clays from the Pacific and had identified extraterrestrial helium-3 in it, attributed to cosmic dust. And in the early 1980s, Ozima and co-workers had actually started down the road of looking at variations in the flux of this component through time. But relatively little was done with this topic. And I think it was partly because most people in the noble gas community, including me, believed it was extremely unlikely that these particles, which are not the most chemically stable minerals that you can think of, nor are they very large, it seemed very unlikely that the helium would be preserved over geologic time. What I'll show you is that, in fact, it is. The helium is retained for reasons that I have to admit are not entirely obvious to me, for at least hundreds of millions of years in seafloor sediments, at least if they are not heated significantly. Burial heating is a problem. So helium is retained, at least in samples that stay cool. Well, it turns out the situation is actually even better than I just said, because not only is the Earth depleted in helium, but the cosmic dust is extremely enriched in helium, because after the dust is produced, it gets bombarded by solar wind ions, which implant into the dust particles. And it turns out you get a concentration contrast between cosmic dust and, say, a ground-up granite, first order approximation of what sediment is made out of about 9 orders of magnitude. It's a very sensitive tracer. Another important point, though, is that we are looking at just the smallest fraction of the cosmic dust flux using the helium. And this is because particles that are bigger than about 30 microns get intensely heated when they transit the atmosphere. Smaller, and their helium is lost to the atmosphere by diffusion or by just vaporization of the particle. The smaller particles have a big enough surface-to-volume ratio that they can radiate effectively, so they don't get as hot. So we're looking at the very tiniest fraction of the tiniest fraction of material that is accumulating to the Earth. in space. Large bodies, bigger than the size of a meteorite, don't deliver helium either. And this is because when they come in, they're vaporized, the helium is launched to the atmosphere, and it never gets deposited on the seafloor. So unlike the platinum group metals, which are tracers of mass of extraterrestrial material, the helium is a tracer of the dust fraction. So it's a nice complementary record. And in the size class of between 3 and 30 microns, we're dealing with Poynting-Robertson drag lifetimes of less than about 10 to the 4th years. Now, with this diagram, I just want to point out how we use the isotopic fingerprint to distinguish the extraterrestrial component. This is just a mixing diagram. On this axis is the helium isotope ratio, and on this axis is the fraction of the helium which is extraterrestrial based on this mixing model. This end member up here, 100% extraterrestrial, is just the solar wind composition with a helium isotope ratio of about 200 times 10 to the minus 6. The end member down here is less well known. This is the terrestrial end member because it depends on the lithium concentration that you assume. However, for this talk, it doesn't really matter very much because all of the samples that I'm going to talk about lie in this region here. So the way you read this diagram is, this is my best guess of the mixing relationship between bulk terrestrial matter and extraterrestrial matter. So one can essentially just measure the helium isotope ratio and read over to get the fraction, which is extraterrestrial. And all of the samples that I'll talk about today are plotting in this gray region, which means that the helium is at least 50% extraterrestrial. And all but a handful of the samples that we'll talk about are at about 95% or more extraterrestrial. So they're all plotting up here. This is a very small factor compared to the magnitude of the signal that I'm going to show you. So I can prove that the helium is extraterrestrial at a pretty good degree of certainty. And the small degree of uncertainty that's left is not important. So I can detect the helium by helium isotopes. To convert that into a flux, I use a dilution relationship with the sediment in the sedimentation rate. So what you see here is the dilution relationship. It just says that the extraterrestrial helium concentration is equal to the flux divided by the sediment mass accumulation rate, which is independently determined. And for what I'm going to talk about today, the mass accumulation rate is determined primarily from magnetostratigraphy. Relatively low resolution, but sufficient to show you what it can show you. A couple of caveats with this method. I'm assuming that there's no helium loss and no particle focusing. These are very important issues for looking at very small or relatively small signals, but again, are not significant for the very large signals, which I'll show you. An additional factor is that we have to deal with the nugget effect. I told you there weren't very many particles present in the sediments, so that you could never count them. Well, we can actually see the statistical effects of a small number of particles. If I take 2 aliquots of the exact same material that have been homogenized, and I analyze it once and I analyze it again, I often get quite different answers because of the statistics of the small number of particles that are there, just a counting statistics problem. So this is a challenge to deal with, and it means you need to get as much mass analyzed as you can to try to beat this effect down. So the way we deal with this is we analyze large samples that are typically in the range from 1 gram to 3 grams. We analyze sediments that accumulate slowly because they'll have a higher, larger number of particles. We replicate individual samples. This is sometimes limited, for example, with material from the ocean drilling program. They don't want you to consume every bit of the core. So we also smooth the temporal trends. So the record that I'm going to show you is highly processed. If I showed you the raw data, you'd see that there's a lot of jagginess. But at the end of the day, again, the signals are large, and that jagginess is not a major concern. Okay, so I'll just skip to the chase here. This is the result of more than 1,000 analyses of sediment. We take the sediments to the lab, we fuse it, we analyze the helium by mass spectrometry. And this is the result. So what you're looking at here is time. This is the age of the sediment, and the flux of helium-3 in femtomoles per square centimeter per kiloliter. These are from 4 different locations. 2 of them are from the deep sea sediments that are exposed now in the Apennines. It's the Gubbio section and also Massigliano. And also 2 ocean drilling program sections from Site 757, which is in the Indian Ocean, and Site 926, which is in the Atlantic Ocean. The immediate thing that jumps out at you when you see this are the 2 large spikes of the late Eocene 35 million years ago, and the late Miocene 8.2 million years ago. And those are going to form the basis of the rest of the talk. These wiggles in through here, I don't actually know what their significance is, if anything, because at that level, at the level of these wiggles, you start to worry about how good the sediment mass accumulation rate is, and you're worried about the other assumptions that I mentioned, for example, particle focusing, things like that. So I'm not sure what any of these wiggles mean, and especially this region in here, which is based solely on Site 757, is uncertain because this part of Site 757 has a very poor chronostratigraphy. It does not have good fossil assemblage. So I'm just going to focus on these two big events in the Eocene of Mars. And I'm going to digress a minute and talk about the 8.2 million year event first. But what I'm going to talk about instead of my work is work that was being done simultaneously, totally independently, without my knowledge, by astronomers. And these astronomers were interested in the history of asteroid families. So let me define this. An asteroid family is a collection of asteroids which are related to each other by the fact that they were produced by collision. There are many asteroid families, and they are identified by plots like this. So this is just a plot of two of the orbital characteristics of an asteroid. In this case, it's proper inclination against semi-major axis. Every one of these dots is an asteroid. And now you realize that, boy, the astronomers have a real advantage over the geochemists. They got a lot of data here. And this is because, of course, they are greatly interested in the threat of these things colliding with the Earth. So there's a lot of effort placed in getting the orbits of asteroids. Anyway, what you see when you plot these are these dense regions, and these are the asteroid families. So these are collections of asteroids that were produced by a collision, and they have the names which are stuck on here. So how do these families work? Well, this is a little movie that I borrowed from Goldschmidt2009. And what you see plotted here are two orbital characteristics, semi-major axis and eccentricity, of a bunch of family members. And the red dots are this family. This happens to be something called the Coronis family. And this is the time evolution of how Goldschmidt imagines that these things evolve. At time zero, there's a collision, and the fragments are moving at relatively small relative velocities. So they spread apart from each other relatively slowly. And that's what the yellow lines are showing you. But one of the things I want to get across here is watch what happens. Watch the clock here. What happens is, eventually, these objects hit a resonance with the giant planets and are slung out and can become potentially Earth-crossing. Before that, they cannot become Earth-crossing. There has to be a way for them to get ejected. So what you're supposed to get out of this is to watch how long it takes for that to happen. This is one particular case, but it takes almost 200 million years for these objects to be kicked out in this particular case. So here we have a time separation between the dust, which will arrive at the Earth within about 10,000 years of a collision, and large objects, if they ever become Earth-crossing and collide with the Earth. It could take several hundred million years. The exact timescale depends on where this collision occurs in the asteroid belt, but it is at least 1 million years, if not tens of millions of years before that happens. So there's this time separation between the big objects and the dust, which is a key to the interpretation of the work that I do. So this group, led by Bill Bottke and David Nizvorny, was interested in the history of asteroid families, and they took all those orbital characteristics of the family members, and they ran the n-body problem, the orbital dynamics problem, backwards in time. And the result is shown here for one family, which is quite important for my story. It's the Veritas cluster. What you see here, this is just an illustration. This is the relative nodal longitude of the family members. You don't need to understand this in any great detail except for to understand that this is the time evolution from 0 to 20 million years ago, and each one of these lines represents a family member. And what you're seeing is that the individual family members intersect in this region here. And that's also shown here, this is the minimum in the dispersion among all of these family members. And the interpretation of this is that this is when the collision occurred, and everything just radiates away from this point in time. So, using this orbital dynamics model, Nizvorny et al. Concluded that Veritas was destroyed, the parent body was destroyed at 8.3 plus or minus 500,000 years ago. This is a very big object, it's 140 kilometers diameter. So that is a very large asteroid that was essentially catastrophically destroyed in a single day. It's by far the largest family forming event that this group has discovered. And what they wrote in their paper on this topic
is that if our hypothesis is correct, we would expect an enhanced abundance of helium-3 in 8.3 million year sedimentary layers, the time when this family was produced. That's a very nice prediction because it turns out to be true. And there's something that, at least when I read this sentence, I get the feeling that they were thinking there would be a spike. But there's not a spike. There's something else going on here. So in fact, simultaneously, I had already actually produced this data, and I had no idea what to do with it because I just had a peek, and I had no idea how to interpret it. And eventually I was put onto this paper, which was in a journal I don't ordinarily read in astronomy, and made the connection and started a collaboration with these guys to better understand this event. So this is the record of this event in the helium-3 from these two ocean drilling program sites. What you see is that they are quite well correlated. So this is a global event. These things are half a world apart. And I can match them up quite confidently because there's some very distinctive microfossils that exist right at the peak. So that's a nice way to be able to tie them together. And this is the only substantial event between 35 million years ago and 2 million years ago, and its age is in excellent agreement with that prediction for the Veritas collision, which is indicated on the top there. So that seems like a nice confirmation that, in fact, the orbital dynamics is correct and we can detect the helium when it arrives. So the biggest collision event in the asteroid belt known within the last 72 million years, and there are no craters of this age, but that's not a big problem because we wouldn't expect there to be, because it takes a long time for the big objects to get kicked out of the asteroid belt to arrive at the Earth to become craters. So that fits together okay. What doesn't fit together okay, at least not without some thought, is that since the sweep out time is certainly less than 200,000 years, and what I've done here is I've actually just cast this onto a time scale where 0 is the peak. And you can see that this event lasts something like 1 million or 1.5 million years. There's a baseline flux, there's the event, and then it decays away. It's hard to tell exactly when it gets back to baseline. In fact, David Nesvorny believes that a substantial fraction of the dust accumulating to the Earth today, maybe as much as 40%, is actually still derived from this collision. In any case, the question is, why is the dust still being produced? It's not a spike. So I worked with Bill Botke and David Nesvorny to model this in terms of a collisional cascade. And this is, in one sense, a plausibility exercise. We did learn something about the way that fragments behave. What we believe is going on is that after the collision, you produce lots of smaller objects that continue to collide with each other over many millions of years to produce this. So this fits the data reasonably well, but there are tunable parameters. We could make it look like pretty much anything. So that's a nice confirmation that it's plausible, but I wouldn't put much more stock in it than that. But I think all of that hangs together as a reasonable explanation for this event. So now I'll move on to the 35 million year event. So the 35 million year event was recognized long ago by several different kinds of observations, which all indicate an unusual flux of extraterrestrial matter at this time. There are 2 layers that contain indicators of impact of many different types, and there are 2 large craters, Papagai in Siberia, and a crater that forms part of Chesapeake Bay. These are the 2 largest craters by far produced in the Cenozoic era. And it was proposed, maybe 15 years ago, that these could be the result of a comet shower. And there were a number of papers on this topic that investigated what should happen when a star passes close to the solar system. And at the end of the day, the conclusions of these papers were, well, it could be, but it's completely dependent on the statistics of this. It is statistically unlikely that these 2 events are not related to each other. And if they are related to each other, the best way to do it is with a comet shower. However, geologic time is long, and statistically unusual things should be expected to happen. So statistics are not a good argument. When I first started making these measurements, Gene Shoemaker came to my office. It's a man that I did not actually know before this. Gene Shoemaker showed up in my office and he said, "You are going to prove whether or not this is a comet shower." And he proposed this very simple test, that if a comet shower had occurred, then the cosmic dust flux should be elevated above the background for the duration of the shower, because the comets are producing dust throughout their lifespans. And in fact, this is what we think is going on. So going back to this event here and blowing it up. So this is a record, again, from these 2 different sites. By far, the best one comes from the type section of the Eocene-Oligocene boundary at Massignano in Italy. That's the gray one with the red top. This section is particularly nice because it includes right here an iridium spike. There's also shock quartz and microspherules. The impact location is very well known in this interval. And it's perfectly correlated with the ages of the impacts determined by argon-argon and the peak of the helium-3 flux. So clearly, this event is related to the big impacts. We also see this in another core in the Pacific at low temporal resolution. It's clearly a global event. So making the same kind of plot, now making time relative to the peak and the relative flux here, I should point out that both this event and the previous event are about a factor of 4 or 5 elevations over the baseline. What I've done here is to try to see whether quantitatively the comet shower model could explain these results. And what I did is I went back to a paper from 1991 where Hutt et al. Actually modeled the frequency with which comets are passing through the inner solar system, which for them was a proxy for the probability of impact with Earth. But for me, is a proxy for the amount of dust in the inner solar system. More comets, more dust. So they produced the black curve, which has got the axis on the right, the frequency of perihelion passages, and it's just relative here. So I put that on top of my data, and I'm going to be totally honest, I have a bunch of free parameters for how I do this. The first free parameter is where I put the peak, and obviously I just aligned the peak with the peak of the helium-3 data. I also have the control of the amplitude of this. I can stretch it vertically. So I made that fit the range in the data. But what I don't have any control over is the time scale, the rise time and the fall time. The rise time is dictated by the fact that it takes a long time for the comets to come in from the Oort cloud. So what you're seeing here is the shower building. More and more comets are coming in. Eventually, some of these comets start to get ejected on hyperbolic orbits by interacting with the giant planets. So this is the comet shower, the comets being ejected from the solar system or thrown into the sun or something like that. So the rise time and the fall time are completely dictated by orbital dynamics. And you can see that matches the data quite well. This little spike here, I don't know why it's there. Does not actually fit the model. It's unclear what that means, if anything, without doing further work at other sites. In any case, it's an excellent match to a prediction that was made long before the data. So I think that's pretty compelling that that's what's going on here, and we wrote a paper that said that. So these things fit together, I think, pretty well. The multiple large impacts are just individual comets colliding with the Earth, and that corresponds to the time when there is the most number of active comets, so we get the most dust, and the rise time and the fall time look correct. And most importantly, I think, these events should be relatively common. They're estimated to occur over intervals of something like 10 to the 8 years. So I have 72 million years of record, and I got one of these events. That's pretty reasonable. But when you compare these two events, there's something odd. They look really similar. And I have to say, I was pretty disturbed by this when I first made this plot. So now I've just stacked these two events. And you see that they're both about the same magnitude, and they have the same decay time. Well, that would have to be a coincidence if one is produced by a comet shower where the orbital dynamics of comets are what affected it, and the other is a collisional cascade of fragments of asteroids. So this might make one question whether the interpretation of the comet shower is correct. I think the asteroid collision, since we know there was an asteroid collision at that time, maybe that one's pretty sound. So maybe both are asteroid collisions. Well, this idea has been put forward on geochemical grounds recently for other reasons. So now I'm going to talk about work that's been done by others. If one looks at the chromium isotope ratios, where's he going with this? Chromium isotope ratios look different in carbonaceous chondrites than in ordinary chondrites. And the reason for this is not well known, but there is a quite distinctive difference between carbonaceous chondrites and ordinary chondrites. And Alex Yakulyakov and others have analyzed the chromium isotope ratio of the late Eocene spherule beds and found that they look like ordinary chondrites and not carbonaceous chondrites. And they concluded that if a comet must look like a carbonaceous chondrite, then the impact at that time was not produced by a comet. And this would greatly weaken the model for a comet shower because one of the major pieces of evidence, the big impact, would have to be attributable to something else. A similar kind of argument was made by Tagle and Clays based on platinum group elements. I don't think that's anywhere near as robust as a chromium isotope argument. But in any case, this is an issue. And as an alternative, Fritz et al. Proposed the following. They suggested that all of this is due to an asteroid shower, a large number of asteroid fragments. And in order to get the dust, because remember, the dust and the large objects are temporarily decoupled. They needed a different source of dust, and the source that they called on was the moon. This is a great idea because it must happen. At some level, dust produced by impacts on the moon must be accreted to the Earth. So their model was these things collide, asteroid fragments collide with the moon, and they kick off fragments. Some of the asteroid fragments actually collide with the Earth and make the two craters that we see. In order for this to work, so this is essentially basically a thought paper without a detailed model to explain it. And I've just indicated here some of the things that must be true in order for this to count for our data. It requires literally hundreds of impacts over a 2 to 3 million year period because the dust will be swept out on a 10,000 year time frame. So in order to keep the dust flux up, you have to keep just banging on the moon to do this. And it somehow must produce a fairly smooth signal in the sedimentary record. This may be possible, I don't know, but one would have to develop a model to explain it. So I think this is a really interesting idea. It requires further work, and I think it requires further geochemistry to understand what the nature of comets really is. Is it true that comets must look like carbonaceous chondrites? I don't know how we will ever know that, but it's clearly an important question. So the conclusions here then, I'll just point out a couple of new things that I haven't said already. This event was at 8.2 million years, almost surely because of this Veritas collision. And when you stack these two records, you notice an interesting distinction between the two events. This asteroid collision looks like an instantaneous event. Nothing's going on, and then bang, and then it comes down. When you compare that to the late Eocene event, you get this much slower rise time. I think this is actually a good argument in favor of this being a fundamentally different kind of event. They look similar, but this is quite a diagnostic distinction between these two, I think. The other thing about these is, as I push this record farther back in time into the Cretaceous, it's going to get harder and harder to find other kinds of information to help interpret the signal. And so this is one way, I think, to distinguish among the possibilities, is look at this rise time. So I'll just conclude by saying that the lunar impact mechanism, I think, is a really good idea in the sense that it must happen. And it raises some important questions that I hope ultimately will be modeled by people that can deal with the very complicated physical processes that are involved. It probably can yield a very high flux of dust to the Earth because the moon is very close, and the Earth will just act as a vacuum cleaner to suck up that dust. The moon has a lot of helium-3 on it because the surface has been exposed for a very long time to both cosmic rays and to the solar wind. But we want to know how frequently these events occur and how much dust do they produce. What is the grain size? We would be very sensitive to a millimeter-size grain of lunar dust in sediments. It would produce a huge signal compared to the background signal. So we should expect to see some statistical effects from that. And I'm quite interested to see whether we see this in the geologic record. And as I just mentioned, what we're doing now is pushing this record into the Cretaceous. We got half of the Cretaceous done. It's too early to tell whether there's anything significant there, but it seems likely that there will be. So I will stop at that.